This is our ECE 2031 peripheral project demonstration. Our project uses a switch flip counter peripheral designed to make tracking switches activity easier in SCOMP. Instead of having the software constantly check for changes, the peripheral counts each switch flip directly in hardware. Every switch has its own counter, and those counters can be reset whenever needed. It can be configured to counting rising edges, falling edges, or both. It also includes a built-in debouncing filter to prevent one physical flip from being counted multiple times. SCOMP can then read both the flip count and the current switch state through the normal I/O interface.
Our peripheral uses registers 06 to 09 for the 10 counters, 6A for the current state of the switches, 6B for direction configuration, and 6C for reset mask, which resets multiple counters at once. We have 3 directions available. When config is 0, the counter will count at the falling edge of the switches. When config is 1, the counter will count at the rising edge. And when config is 2, the counter will count at both directions. To use the reset mask, we just need to set a corresponding bit to 1 and write that to the reset mask register.
The peripheral is used by the programmer like any other SCOMP peripheral, but with multiple read and write addresses. Each counter has its own address, and only one counter can be read at a time, although all counters are counting simultaneously. This peripheral is backwards compatible with the old switches peripheral, using the switch state address. Writing to the flip direction config does not reset the switch counts. The programmer must either write any value to the individual counter or write to reset mask with the respective counter bits set to 1. Let's look at 2 examples of using the flip counter peripheral. On the left, we can see how to configure the flip direction and using a reset mask to reset multiple counters at once. The value 2 is loaded and written to the config, which sets the flip direction to both. A reset mask, consisting of all bits set to 1, is written, which resets all flip counters. On the right, we can see how to read and clear individual counters. Getting a count is as simple as reading a counter address. Writing any value, including 0, to an individual counter address will reset that counter.
Implement the counter. We store the previous state and the current state in 2 signals. At each clock tick, we update the signals and compare previous state to current state. When a transition is detected, we update the count based on the configuration selected. If we want to reset a counter, we can write to a specific counter or do it through reset mask to reset multiple counters at once.
Our demo game is called Flip Race. How it works is the player turns on switches 9 and 0 to start the round and timer, then flips the switches as quickly as possible. The peripheral counts every flip directly in hardware, while SCOMP reads those values and updates the display. Switches 4 and 5 are used before the game to configure which flip direction will be counted. When switch 4 is up, it is falling. When switch 5 is up, it is rising. When both switches are down, it counts in both directions.
Let's demonstrate the peripheral by playing a few rounds of Flip Race. Before we start the game, I will set the flip direction configuration to rising by setting switch 5. Now both players set their switch to the ready position and wait for the countdown timer. The scoreboard updates to show the player's live score. The round is over. Let's try a different flip configuration. I press the reset button to start a new game, and set switch 4 and 5 to select both rising and falling. Watching the scoreboard closely, the debounce filter ensures that each flip is only counted once. At the end of the game, the scoreboard freezes indefinitely until the reset button is pressed.
So beyond our flip race demo, the same peripheral pattern can apply anywhere SCOP needs reliable event counts from digital inputs. The main idea is that the hardware handles edge detection and counting instead of forcing the SCOP program to constantly pull switches and compare old values to new values. That can be useful for games, program configuration, simple user interfaces, or dynamic switch behavior where transitions matter more than just the current switch position. So while our demo is a race, the reusable concept here is edge detection, hardware counting, debounce filtering, and a memory mapped API that software can access through normal in and out instructions. To conclude, our peripheral successfully extends SCOP with hardware switch transition counting. SCOP can still read raw switch states, but it can also read individual per switch flip counts. The config register selects whether the peripheral counts falling edges, rising edges, or both directions, and reset mask lets the program clear selected counters before a round begins. In our demo, the switches are used to start the flip race and select the count configuration, while the peripheral handles the actual counting and hardware. Overall, the live demo validates that our SCOMP software and custom hardware peripheral are working together through the I/O interface.